Good afternoon, folks. How are you today? We will continue today with numerical integration or quadrature. Again, want to remind you, our goal is given a, b, and a function of x. We want to find the integral from a to b when the function is integrated with respect to x. So we covered a bunch of methods. We started with trapezoidal rule. So we said we are going to divide the interval AB in equal width strips, and that equal width is h. So we found out that in trapezoidal rule, our area was approximated as h by 2 times a weighted sum of function values. And these weights were 1 on each end and 2 at all the points in between. So if you look at trapezoidal rule, we said area is h by 2 times the weighted sum. So if we combine these two, basically area is a weighted function of values. So this is what we are going to see throughout. That all the method is basically how should we weigh the function values and sum them, and that turns into the area. And of course, with trapezoidal rule, we found out that our truncation error was proportional to h squared. Then we covered Simpson's rule. And in Simpson's rule, we found area was h over 3, again times a weighted sum. But this time the weights were different. This time the weights were 1 and 1 on the each end, same as trapezoidal rule, but in between they went from 4 to 4 to 4 to ending up in 4, since we have a odd number of points. We have even number of strips, but we have odd number of points. So again, if we move this h by 3 factor inside and incorporate it into weights, again our area becomes basically a weighted sum. And this time our truncation error is proportional to h to the power 4. So just by changing weights, notice we can reduce truncation error, and that's a very big key. Of course, then we went on to look at Romberg integration, and we said we can improve upon area approximation if we know the error behavior. So let's say for this area estimation, any of the area estimation, we know the error behavior, this power m. Then what we can do is we can use two different strip sizes to evaluate the integral. And then knowing this error behavior, we can again do a weighted average of these two area estimates using thin strips. Thin strips are with h2 spacing, and thick strips which are with h1 spacing. And remember, when we did examples, just for convenience, we chose this ratio to be 2. Now, this A beta has a truncation error that is proportional to h to the power m plus 2. So every time we do this averaging, Richardson extrapolation, we improve upon our truncation error by a factor of 2 in the exponent. And we can use this method anywhere, this idea of Romberg integration. It is just how we can improve approximation, don't need to be necessarily area if we know the error behavior of our approximation. So later on, we are going to see how we can use this idea when we solve ordinary differential equations. And then, of course, I mentioned to you that if we have more strips, so as H decreases, we increase the number of strips, we decrease the truncation error. But of course, if we decrease H, increase the number of strips, we do more calculations, we do more summations. So we increase the round off error. So as we see in this graph, as H decreases, as H decreases, you can see truncation error decreases. Now this person has drawn it as a straight line. It need not be a straight line. So I drew it as a curve. So I said H decreases, truncation error decreases. But round off error increases. So when we look at a total error, the total error has a minima somewhere here. So that means if we use too few strips, truncation error dominates and error is large. Too many strips, round of error dominates and error can be large. So we got to be careful. We shouldn't use too many strips or too few strips. And we'll see how we can look at that when we are analyzing our data. Okay, the next method that we are going to talk about is Gauss quadrature. Before I get into the method, I want to say something. This method was not taught for a long time in traditional numerical methods courses because often the machines that we use, slide rules or hand calculations or log tables, didn't have sufficient precision. And this method is excellent if you have data that is of sufficient precision and you can do calculations with sufficient precisions. So often we don't have data with sufficient precision because most of our machines that are more than 20, 30-year old still have dials or have LED, LCD display that only display limited number of digits. But as we are computerizing more and more of these equipment and machines, we are collecting data as good as computer's precision. So now we have both data collection ability, so we have data, and we can do computations both in high precision. When I say high precision, I mean 7 digits or more. So of course, computations you have seen, we are just routinely doing in 15 digits in Excel. And if we can get the data using computers, we have at least in 16-bit systems, we have easily 7 digits of data. So I am teaching Gauss quadrature because it's an excellent method and you will see its power in a few minutes. Okay, so let's suppose that we wanted to calculate area of one strip. And between A and B, this is X. And our curve looks something like this. So if you use trapezoidal rule, our trapezoidal rule is going to underestimate this area. However, let's suppose if I was allowed to use trapezoidal rule, but at my own chosen nodes. So I'm going to choose 2 nodes again. I'm going to do still 2 function evaluations, but at my own choice, x1 and x2. And I'm always going to choose x1 and x2 relative to AB like this. And then what I'm going to do is, to these 2 function values, I'm going to fit a straight line, and I'm going to build a trapezoid again on this entire width. So this entire AB width. But as far as the height is concerned, I'm going to average these two values rather than the values at the end. So you can see the new trapezoid that I have drawn, which is shown at the bottom here. So this is my trapezoidal rule, and this is going to be my Gauss quadrature rule, where I select x1 and x2 myself. Okay, let's see the next picture here. Next picture here, this time we do the same thing, AB, but our curve is concave up. So now when we do trapezoidal rule overestimates. But if we do our same x1 and we do same x2 and use these two lines to build a trapezoid, you can see I make much smaller error. So that is shown in these two diagrams. Let's try a third diagram. Here the shape changes. So when we do trapezoidal rule, of course, trapezoidal rule in my figure is doing a little slightly bigger overestimation because it is balanced here. No, underestimation, I should say, underestimation. But same thing, I do x1, x2, evaluate the function, build my trapezoid, and you can see in this diagram here, the Gauss is doing a little tinier, much tinier overestimation than underestimation than trapezoidal rule. So the key idea here is, if you allow me to choose my own nodes, so as to say, Gauss quadrature does a better estimation. So let's see how this works. So again, we are going to do area estimation using Gauss, again using weighted sum. So we are going to do weight times function. And we'll have some points, 2 points to begin with, but we can maybe even have 1 point. So let's suppose that we want to evaluate our integral fx dx from a to b. What we'll do first is we are going to transform this into a very standard integral. We are going to say our integration limits are always from -1 to +1. So we need to transform this function so we have an equivalent integral. So let's suppose we transform it. We'll worry about that later. So now instead of evaluating this, we are going to evaluate this. And we'll talk about what this function gz is later. So if we are given n data points, what we are going to do is we are going to say area of Gauss now is summation of wi times function at zi. So remember, previously it used to be fi, but now our integral is in gz term. We are evaluating this integral here, right? So we have n points. So what we want to know is, for points that are numbered 1 through n, what is wi equal to? And what is zi equal to? Because we know the function gz that we want to integrate. So it turns out, since our integral range is from -1 to +1, z belongs in this range -1 to +1. And our weights are in the range from 0 to 1. Okay. So the key question is how to find them. So let's consider the simplest of the case. Let's consider, well, actually n is equal to 1 is simpler, and you will have a quiz question on that. But let's consider n is equal to 2. We have 2 points. So now we want to find out the values of, we have 2 weights, W1, W2, and we have 2 nodes, Z1 and Z2. So we have 4 parameters. Since we have 4 parameters, what we can do is we can fit a polynomial of size 2n minus 1 in Z. So notice when n is equal to 2, this is our polynomial of third degree. A polynomial of third degree has 4 unknown coefficients. So since we have 4 parameters, that's why we are fitting a third degree polynomial. And it'll turn out that our area estimate would be exact if GZ is a polynomial of up to that degree. So if we fit 2 points, a third degree polynomial, if GZ is either first degree, second degree, or up to third degree, our area estimate would be exact. So what we are going to do is, since we have 4 parameters, we are going to set up 4 equations in those 4 unknowns, these 4 unknowns. So our third degree polynomial looks something like this. C1 plus C2 times Z plus C3 times Z square plus C4 times Z cube. And our method should work for any combination of C1, C2, C3, C4. So what we are going to do is, immaterial what C1 is, we want to get exact result independently. That's how we are going to set up our 4 equations. So let's take GZ is just 1. So we integrate minus 1 to 1 times dz. So we will get z from minus 1 to plus 1. So we will get plus 1 minus minus 1, so we'll get 2. So integral of gz dz, remember, from minus 1 to plus 1, we would have written as w1 times g at z1 plus w2 times g at z2. But our function gz is 1, so this will just become w1 plus w2. So that's our first equation. Next, let's consider the second term. So whatever c2 is, we don't care. Any integral of z will be like this. So we'll do z square over 2 from minus 1 to plus 1. This will come out to be 0. Now our function is z, so our integral would be like that. That's our second equation. Let's take our third term here, z square. So we'll evaluate minus 1 to plus 1 z square dz. We'll get z cube over 3 from minus 1 to plus 1. So this will be 2/3. Now w1 times z1 square plus w2 times z2 square. Then we have gz is equal to z cube, last term, this last term, -1 to +1, z cube dz is z4 over 4 from -1 to +1. So this will come out to be 0 again. So you see we have 4 equations here involving 4 unknowns that we want to find out. W1, W2, Z1, Z2. So W1 comes out to be 1, W2 comes out to be 1, Z1 comes out to be -1 over square root of 3, and Z2 comes out to be +1 over square root of 3. Right? So this is for n is equal to 2 points. Okay, so that was a lot of work, but for 2 points, we got the weights and we got the nodes at which we need to evaluate our function to get the integral value. Now, of course, this derivation has been done for different number of points. So you can go in a handbook or look it up online. So these are called Gauss Legendre nodes and their coefficients. Coefficients are the weights. So these are roots of the polynomial. So 2 points, you saw plus and minus 1 over square root of 3. Both the weights are 1. So if you look at the even number, so here is z, here is gz. We want to integrate from -1 to +1 some function, let's say. So we want to find this area. This is what our goal is. So what we are doing is, if we have 2 points, -1 over square root of 3 plus 1 over square root of 3, we evaluate the function gz, and for, of course, 2 points will be fitting a trapezoid, sort of. But the idea is, when we have 2 points, they are located symmetrically with respect to the origin, with respect to 0. Now let's look at when we have 3 points. When we have 3 points, the middle point is always 0, and then this time we have 1 point on either side. You can see plus and minus square root of 3 over 5. Okay. When we have 4 points, of course, we have 2 points to the left of 0 and 2 points to the right of 0. They are symmetrically located, and notice their weights match. The more we are to the interior, the larger the weight is. The more we are towards the extremities, -1 or +1, the weights are lower. Okay. What about the truncation error? So it turns out that the truncation error here is 2 to the power 2n plus 1. Remember, n is number of points. N factorial to the power 4 over 2n plus 1. And then we have 2n factorial cube. And then the derivative is of the order 2n. We evaluate at zeta. And of course, zeta is between -1 to 1. Okay. So this should be actually less than equal to, less than equal to. Okay, so far so good. So we know how. So remember, this error is for this integral. But we wanted to integrate fx dx. So we really wanted to integrate a to b fx dx. But instead we learned a technique to integrate gz dz. So we need to do this transformation. So how do we do this transformation? We'll do a linear transformation. So we'll say x is sum p times z plus q. Okay. So let's see what we mean by it. So here is our z from -1 to +1. Don't worry about this vertical line. Okay, this does need to be 0. Here is x, which goes from a to b. So we want a to be -1, b to be +1, and we want a linear transformation. Okay. So therefore, at z is equal to -1, x is a. So we can write a is p times -1 plus q. At z is equal to +1, x is b. So b is p times +1 plus q. So again, we have two equations, two unknowns, and we can solve for p and q. So p is b minus a over 2, and q is b plus a over 2. Does it make sense? So let's see. This is slope of the line. So let's see what our slope is going to be. Height is b minus a, width is 2, b minus a over 2. This is our intercept at z is equal to 0. So if you look at z is equal to 0, this intercept here is going to be the average of these two values. Average of these two values. Okay. So if we write dx, dx would be p times dz. So now we can go do the replacement. We want to integrate from a to b f of x dx. So this is equal to our a becomes -1, b becomes +1. Function x is pz times q. Well, p is b minus a over 2 times z plus b plus a over 2. That's our x. And then dx is p times dz. P is b minus a over 2 times dz. So this whole thing is called gz, right? So therefore we can write gz is, this is a constant factor, b minus a over 2 times function of b minus a over 2 times z plus b plus a over 2. Okay. So let's apply it to our example problem. So let's say we want from 0 to 0.8 e to the x dx. So our function of x is e to the x. Of course, a is 0 and b is 0.8. So what is our b minus a over 2? That's 0.4. b plus a over 2, also 0.4. Maybe I should have chosen a different limits, but I'm sure you can keep track of things. Okay. Okay, so what is our GZ? B minus A over 2 times the function, which is E, 0.4 Z plus zero point 0.4, right? P times Z plus Q. Okay, so we can kind of simplify this. We can write this 0.4 E 0.4 times E to 0.4 Z. All right, take your calculator out and calculate with me. So we'll make a table. 2 points. We have weight, we have ZI, we have GZI, and we can weigh these function values. Okay, so we'll keep 7 digits. Our weights are 1 and 1. So we are going to do 1 over square root of 3. And we'll get 0.57735, and I'm going to round up 0.3. So negative and positive value. Okay, now you type in 0.4 e to the 0.4 times e to the 0.4 times z and calculate it in your calculator. I hope you get 0.4736764. Similarly, calculate at this positive z value 0.751750. Then we can multiply these two in our calculators, total them up, and we'll get 1.2254271. So that's our Gaussian approximation. Okay, let's see what is our true value. Is 1.2255409. So notice we match 225, and then these digits starts differing. So let's see what's our actual error. So we subtract one from the other, we get 0.00012. All right, let's see what is our truncation error bound. Okay, so let's bring up our formula for truncation error. Right, so we have n is equal to 2. Let me bring another page here. So our truncation error bound is going to be 2 to the power 2n plus 1. N was 2, so it will become 2 to the power 5 times 2 factorial to the power 4 over 2n plus 1 times 2n factorial. That's 4 factorial. 4 factorial is 4 times 3 times 2, 24. Cube, right? And then notice our function was that g, so we need to take second derivative of that. So let's go back to our function. So our function g was 0.4 e 0.4 times e 0.4 z. So when we take first derivative, remember we need fourth derivative. So this one will give us 0.4, same thing. Then we take second derivative, this will become square. Third derivative, this will become cube. Fourth derivative, this will become to the power 4, right? And we know that this would be maximum where z is maximum. Maximum z is plus 1. So our second derivative here would be, so let's bring this here. So we have this term, 0.4 e 0.4. Notice I'm doing same thing on this slide here. Then I'll have 0.4 to the power 4 and then e to the 0.4 at z is equal to 1. So we will get 0.00017. So this is our error bound. This is what we would have predicted, plus minus. And remember, our actual error is only 0.00012. So it is smaller than this, which is what we expect, right? Okay, so a lot of work, but you can see just with 2 points, we were able to get 3 decimal digits, correct decimal digits, which is fantastic. But we require a lot of precision in our data and in our calculations. So let's see same thing if we were to go do 3 points. So remember, we have transformed our example problem. This is e to the power x dx. So we have transformed it from fx to dz. If you look at the table, when we have 3 points, our z can be 0 or plus minus square root of 3 over 5. So if you do square root of 3 over 5, you will get to 7 digits, 7745967. And then of course our weights are 8 9 and 5 9s. So 8 9 is 0.88888 rounded up 9. 5 9 is 5555556. Okay. So please do this using your calculator. It's just that it is easier for me to type it up in a tabular form. So here are our weights. I just wrote them here. Okay. These are our nodes. We calculate our function. Remember, this function is this whole thing. Then we weight the function, sum it up. So this time 2255409. Notice the true value is 2255409. So we don't even know what the actual error is, but actual error cannot be any more than in the last digit, right? So it's 0.5 times 10 to the minus 7. If we use the formula, just like what we just did a few minutes ago for n is equal to 2, the only thing that is going to change are these numbers. And of course, this will become 0.4 to the power 6 because we need sixth order derivative. So we would have predicted an error bound 2.3 times 10 to the minus 7. Of course, larger than actual error. But we can see we are reaching the limit of Gauss quadrature if we can only keep 7 digits. Because if we go to n is equal to 4, now 7 digits won't be enough for Gauss quadrature to give a reasonable value.